Okay, I hope I'm audible as well as visible. Um, I'll begin in 5 minutes. So I've shared a mm, data handbook with you guys, and that contains all the details about, I would say, the complete heat transfer module, wherein not just the natural convection and the forced convection and other things, like, for example, internal flow and those things have been discussed, but also conduction, radiation, and such stuff. Those equations have been discussed because there are like a lot of correlations which exist um, in heat transfer module, because different people have tried to experimentally determine the Nusselt numbers or heat transfer coefficients with a lot of experimentation, and that is how, with a lot of experimentation, they've developed many correlations which approximate the Nusselt number or the Rayleigh number or the Grashof number. And so in this data book, they have just compiled all such values for different cases, which has been very nicely put over there. So I'll be referring to that while discussing the problems on this section today and for the upcoming sessions as well. I feel this uh, handbook is very, very helpful personally for me as well, because when I was doing my bachelor's, this is what my prof, the prof who taught me, his name was P. Srinivasan. He shared this data book with us, and once I got this, I got like hooked to it. Every time heat transfer was the module which I liked the most, I think, and that's why my research also in my PhD is related to heat transfer. But it seems like once I got this data handbook, I did not go back to referring to the textbook every time when I had to solve problems. This data book was all I needed. So again, I think we don't have any uh, participants as of now. Hopefully, someone will. Hopefully, people will join by 7:05. Let's see. If anyone watches the recording, I'm just curious. Are you guys like busy these days? Because like, are you guys are like done with my sessions, PDB sessions here, or am I boring you guys too much? What's happening? Because like very less people are attending. I'll anyways record every Thursday and then upload so that those who watch the recordings can go through it later on and then go through the content as well. Today I'll be discussing free convection. So I hope the screen is visible and everything is okay. The audio as well. So and free convection is the topic for today. Um, Let me first go through the theory. I think there's almost negligible theory in this part because there are just correlations. I'll still go through a few things. Let me see. Okay, so I think I'll begin with the Grashof number. So can I have a thinner pencil? Yeah, this looks better. So I'll begin with the Grashof number. So usually in natural convection, there is a dimensionless number which is called the Grashof number, and Grashof number is uh, the buoyant force over the viscous force. So the correlation, I mean, the equation goes like this: Grashof number at any length L is G times beta times temperature of surface minus temperature of surrounding times the cube of the characteristic length over uh, nu square. So this is like the Grashof number. Apart from this, there is Rayleigh number. Uh, Rayleigh number is defined as higher when I'm discussing free convection today. Rayleigh number at any length L is Grashof number at any length L times Prandtl number, which is again G times beta times Ts minus T infinity times LC cube over nu square. I think these are the only two correlations which are there commonly for the free convection. Apart from that, there are a lot of formulas which exist, but those are for very specific cases. For example, for vertical cylinders, vertical flat plates with isothermal surface with constant heat flux, there are like different correlations, but we'll go through some of them during the questions which I'll be discussing. I've shared three questions on the Teams group which we have. Uh, and I would like to directly jump to the questions today. I think that's all what I've got for the theory this time. So let's begin with the first question. Let me see which one will I post. 9.14. So this is the problem. I have also got the properties of different materials. Put it here. Okay. So this problem is technically it says an aluminum alloy plate heated to a uniform temperature of 227 degrees Celsius is allowed to cool while vertically suspended in a room with the ambient air and surroundings at 27 degrees Celsius. Okay, so we have a aluminum alloy. Okay, it has a thickness as well. So this, then this. So we have a vertical plate, and its thickness is defined as this is how much is this? 0.3 meter. Oh, 15 centimeter. Okay. Thickness is 15 centimeter and area is 0.3 meter square, and emissivity is also given. Emissivity is 0.25, and temperature, it's a constant temperature case of 227 degrees Celsius. This is Ts. And then we also have T infinity as 27 degrees Celsius. So this is a very simple free convection case wherein there is a vertical plate which is being hanged at a constant temperature of 227 degrees Celsius. We'll assume that the temperature remains uniform all over the plate because it is aluminum, so it's very, very conductive. They are asking us to develop an expression for the time rate of change of the plate temperature, assuming the temperature to be uniform. Okay, they are also saying that the temperature will be uniform. So I'll pause for a minute for you to think, and then after that, I'll begin. This is not 0.3 meter square, this is 0.3 meter as the side S. So let me do that. The side length is 0.3 meters, and this is also 0.3 meters. So there is obviously there is, because we have been given emissivity, so there is surely radiation happening, and because the plate is hanging, that is why we also have natural convection happening, right? So we write the like the direct equation of energy balance. So the you can say that uh, rho v Cp, which is mCp dt over dt, is the energy change in any time, any small time dt. It is so we are losing heat, right? So we'll put a negative sign because the plate is at a higher temperature and surrounding is at 27 degrees Celsius. So first of all, the free convection term, which says HL bar times. Okay, so it has two surfaces, this one and the one which is behind, right? So HL times 2 times uh, area, area of surface, times Ts minus T infinity. So basically HA delta T multiplied by 2 because we have two surfaces, the frontal one and the one which is hidden from our view right here. So this is the heat loss from the convection term. And then there is also heat loss from radiation, which is epsilon times 2 times AS times. This 2 is again because of radiation from two surfaces times sigma Ts to the power 4 minus T infinity to the power 4, right? This is the radiation term. So mm, this is the convection heat loss, and this one is the radiation heat loss. Now, we have got every value. So I used rho v here. Rho v is technically mass, right? So mCp dt over dt. This is the formula, right? So now for this, what all do we have? Let's find out. We have rho v Cp. Yes, we have everything. We have to calculate dt over dt. So this is the thing which is missing right now. Then there is HL is also missing. We don't know the heat transfer coefficient as of now. And we have two, we have AS, we have TS minus T infinity, we have everything. We have epsilon, we have AS, sigma, TS, T infinity. We have everything. What we don't have is these two terms, right? This and this. dt over dt is what we have to figure out. So let's calculate HL first, the heat transfer coefficient average over the whole plate, right? How do we get HL? it can be calculated using the correlations for Nusselt number and the Rayleigh number. We can use those. So let's usually in such problems you first calculate the Rayleigh number, and from that you use the correlation for Nusselt number, and from that you get the heat transfer coefficient using NUS. So okay, there is one more equation which I forgot to mention here, which is NUS HLC over K. Okay. So these three equations are the ones which we use, 1, 2, and 3. Okay. Let's first use the Rayleigh number. Let's first calculate the Rayleigh number at any length L. So for a vertical plate, the Rayleigh number is simply defined as RA at any length L is G times beta times Ts minus T infinity times L cube over nu times alpha. Uh, so we are just going to plug in the values. It is G is 9.8. Beta is, how much is beta? Beta is 1 over T, right? So 1 over 400, which is, why 1 over 400? Because usually in such questions, I see many students making mistakes because they consider the temperature in degrees Celsius, whereas we must ensure that everything that we put inside the equations in terms of temperature should be there in Kelvin and not in degrees Celsius. So please be aware of this, especially in the presence of radiation. Because of this term raised to the power 4, it becomes very, very prominent mistake when if you use degree Celsius here in this equation, this value is going to be completely different from the case when you use Kelvin. So that is why this term is very, very important, because this factor is very, very small, 5.67 times 10 to the power minus 8. So you will get negligible radiation if you consider the temperature in degrees Celsius. That is why I always prefer, let's use Kelvin, right? So we get beta, which is 1 over T. And then we have Ts minus T infinity, which is, here I'll use degrees Celsius. So because it is subtraction 227 minus 20, how much is 27 then? Okay. Times L cube, what is L? L is 0.3. 0.3 cube over nu times alpha. What is nu? It has been given in the, it should have been given in the question. Um, nu is 26.41. Okay. 26.41 times 10 to the power minus 6, and it is in SI units. And then we also have alpha, which is 38.3 times 10 to the power minus 6. And we also have Prandtl number. We are going to need it later. The value which I have for Rayleigh number is, okay, I'll give 10 seconds and then I'm going to put in the value. The value which I have got is 1.308 times 10 to the power 8. And this is a dimensionless number, right? So you don't have a unit for this. Now, once we have the Rayleigh number, can we calculate the Nusselt number from this? New bar at L. Now the problem comes to the data book, right? So in the data book, I'm going to go to the PDF's page number 51, which says table C.2.1 natural convection from external surfaces. And in that, I see vertical isothermal surface, which says Nu raised to the, okay, I'll write it here. Nu raised to the power 0.5. I'll write it the other way, okay. Nu is 0.825 plus 0.387 Ra raised to the power 0.167 over 0.167 × 10 to the power 6. 167 over 167 × 10 to the power 6 1 plus 0.492 over Prandtl number raised to the power 0.5625. This is raised to, it's very complex, but it's very, very helpful. 296 whole raised to the power 2. Either you can use this. There is actually a better correlation available, which I'm not sure if is given. It's not there in the data book and it's not there in your textbook as well. But there is another better expression, but I'll not put it over here. Let's skip it. Okay. So from this, if you put in the Rayleigh number value from here and you plug it in this equation, you're going to get NU. There are like a lot of calculations in these problems, and you have to be very, very careful while calculating. So one more important thing is this Nussel number value is valid only for 10 raised to the power minus 1, RA 10 raised to the power 12. Okay. And we have our RA in that range, right? So we can use this. So the value for Nussel number which I have is, how much do I have? Let's see. Okay. So NU which I have got is 55.5. And now from that we can calculate HL, right? HL is NU K over L, which is 55.5 times the thermal conductivity, which is, this is not of aluminum, right? Because we are calculating the heat transfer coefficient of the air. So usually it is taken of the fluid. So air's thermal conductivity is 0.0388. You also have to be aware about which, the formula is fine, but of which medium are we taking the property? And what is L? L is 0.3, right? 0.3. From this, you will get HL bar as 6.25 watt per meter square Kelvin. And now once we have HL, we just have to plug this value into this equation, right? So I'm going to say, what is rho? Let's plug in the values. I'll actually simplify. I'll okay, let's keep it like this only. What is rho? Rho is 2770 times 0.015 times CP. Okay, 0.015 is the volume, which is V is A times thickness, which is 0.3 times 0.3 times 15 centimeter is 0.15, I think. 0.015 or 0.15. This will give you 0.015. Um, and what else have we got? 2770, 0.015 times CP, which is, how much is the CP? CP is, let's see from here. CP is 983. So 983. Uh, and then there is dt over dt is equal to minus 6.25 times 2 times 0.3 squared times 227 minus 27. This is the convection term. Minus epsilon is 0.25 times 2 times 0.3 squared times 5.67 times 10 to the power minus 8 times 2, not 227. Here it will be, This will be times 227 plus 273 raised to the power 4 minus 27 plus 273 raised to the power 4. From if you use this, you're finally going to get dt over dt, which is what they're asking us to calculate, the rate of change of the temperature with time. And what value have I got? Okay, the value which I have is minus 0.099 Kelvin per second. Okay. Oh, we have another part for this problem, right? What's that? It says there's part B as well. Determine the initial rate of cooling when the plate temperature is 227 degrees Celsius. I think it's the same, right? Yes. Well, I mean, we already calculated the rate of change. This is the initial uh, rate of cooling dt over dt because we put in the temperature as 227. Ideally, when the plate is cooling over time, this temperature is not going to be 227. It's going to change over time, right? But we have put 227. That means that we are calculating the initial rate of cooling. Ideally, this is a dynamic equation. It changes over time. So the expression would be this one. You can say this is the expression. And once we have used this expression to calculate the initial rate of heat temperature gradient, which is minus 0.099. It is negative because the temperature is reducing over time, right? So we are done with the first problem today. Second problem. Usually in these set of, especially the topics which are going to come like forced convection and flow in a cavity and such things, usually we just have to rely on the data book and the equations. You cannot do anything. I mean, the standard process would be calculate the Grashof number, from that calculate the Nusselt number, heat transfer coefficient. From that you bring in back to the first equation, and then you calculate whatever is the temperature rate change or whatever they're asking. This is the usual kind of problems which I've seen in such uh, modules. What's the next problem? 9.37. I have the properties as well. All right. An electric heater in the form of a horizontal disc of 400 diameter is used to heat the bottom of a tank filled with engine oil at a temperature of 5 degrees Celsius. Electric heater, horizontal disc. So it's a horizontal disc. Okay. It's a horizontal disc. And 400 is the diameter. So I can say 0.4 meters is the diameter, filled with engine oil at a temperature of 5 degrees. So T infinity is 5 degrees Celsius. Calculate the power required to maintain the heater surface temperature at 70 degrees Celsius. Very simple problem. So we have a constant temperature horizontal plate case. This is what you have to determine in such problems. Very quickly, just see, okay, horizontal plate, and it says constant temperature of 70 degrees. So okay, you know constant temperature case, horizontal plate, what to do. So you just go back to the data book and find out what is the correlation for that, and quickly calculate the Grashof number, Nusselt number, heat transfer coefficient to quickly get the power required. Okay, we'll see how to get to power required in this problem. I'll spare 1 minute for you to think, and then after that I'll begin. We are going to follow the exact same pattern which we followed for the previous problem. Exactly same. Nothing different. Okay, so let's begin the solution for this. So this says that we have a horizontal circular disk, right? So first of all, let's calculate the LC, the characteristic length of it. LC is AS over P, right? Area of surface over the perimeter. What is the area of the disk? It is pi d square over 4. Pi d square over 4. And what is the perimeter? It is pi times d, right? Or 2 pi r. This is pi. So it will be, I think, d over 4. Yes. D over 4, which is 0.1 meters. So we have LC. Let's call this equation 1. I'm going to number the equations from now on because it makes things less complex. I mean, more managed. Now, again, very same approach to the problem. Quickly, let's calculate the Rayleigh number. Rayleigh number at any length L would be G times beta times Ts minus T infinity times L cube over nu times alpha, which would be 9.8 times, what is beta here? Beta would be 1 over T. Uh, it is 1 over 310. I think let's calculate. Let me see once. Later. 310. Um, sure. Okay, that's what I was thinking because beta value is usually the uh, inverse of the temperature of the fluid, but here in this case they have provided the value of beta here, so we have to directly use this value. Beta is 0.7 times 10 to the power minus 3. If they explicitly ever provide the beta value, you just have to use that beta. Please don't calculate using the inverse of temperature. Times Ts minus T infinity, which is Ts temperature of surface is 70 degrees minus 5 degrees times L cube, which is 0.1 raised to the power 3 over V times alpha, nu times alpha. Nu is, what's this nu? 288 times 10 to the power minus 6 times 0.847 times 10 to the power minus 7, right? From this, the value of real number which I have got is 1.83 times 10 to the power 7. Actually, it is 1. You can say 1.828 times 10 to the power 7. I should use approximately equal sign here. I've replaced the sign. So this one would be, I would say, like this, and then actually the value is this. This is the equation 2. Okay. And this is the value of RA at L. Now we have RA, we'll quickly calculate the nozzle number. So NU L average would be, let's go back to the data book, and this is a horizontal cylinder with Give me a sec. Hmm. Horizontal cylinder with uh, Rayleigh number as something 1.8 times 10 to the power 7. Uh, Now, once we have this, I have the correlation Nu as C times Grashof times Prandtl number raised to the power m, which is C times Rayleigh number to the power m. And because we have Rayleigh number in the range of 10 to the power 4 to 10 to the power 9, I guess. 5, 9, right? Hmm. It is in the range of 10 to the power 4 to 10 to the power 9, right? 10 to the power 4 is less than Ra is less than 10 to the power 9. So the value of C is 0.59 and the value of M is 0.25. So we'll get Nu L as 0.59 times 1.828 times 10 to the power 7 raised to the power 0.25. The value of Nussel number, which I have got from this, is how much is Nussel number? 39.5. So this is our equation 3. Okay. Now, because we have the Nussel number, we have the Rayleigh number, and we have the characteristic length as well, we can very quickly calculate HL, right? H bar L, which is K times Nu bar L over LC. Now, how much is K? K 0.145. K 0.14145 times how much is Nu? 39.5. How much is LC? LC 0.1, right? So we are going to get from this the value is 57.3 watt per meter squared Kelvin. So we have now HL as well. Let's call this equation 4. So now we have everything, right? The what are they asking us to calculate? Calculate the power required to maintain a heater surface temperature at 70 degrees Celsius. So we will quickly calculate the heat transfer rate, Q dot. How much is Q dot? It is there is only convection taking place, so which is HL times area of the surface times Ts minus T infinity, right? Which is 57.3 times As is pi d square over 4, which is pi times 0.4 squared over 4 times 70 minus 5, which is how much is this? The value which I have is 468 watt. So this is how much energy would be, this is how much power which is required to keep the heater surface constant at 70 degrees Celsius. Now they might extend the problem a bit further. So usually this is how I've seen such problems. So they're going to say that this is, let's say this is your heater and we are applying a voltage difference of, let's say here is 25 volts, here is 0 volts, and they're going to ask how much current is going to flow from the wire, or they might give you they might ask you the resistance of the wire as well. So from this it's very simple, right? So 468 is V times A, and if we have V, we have 468, we can quickly calculate A. From this we can also calculate R, right? So this is how the problem might get extended. This is a straightforward problem. It's not complicating it much. It's directly asking for q dot. So that's it. um, I'm done with the second problem. Moving on to the last problem for today. See, these problems are quite long to solve. It has already been 40 minutes since I've started this. So each problem I think took almost 15 minutes because 10 minutes went in discussing the theory and the initial set of equations. Okay, I think last problem for today because I'm trying to finish in 1 hour because I have my qualifying examination on 15th, so I have to prepare for that. Okay, this is our next problem. Yeah, I got a good idea. I can share the so my qualifying examination is happening via Teams, so I can share the link if any one of you is interested in my PhD research as well. They can join and just have a look on what all I'm working on. It's majorly related to heat transfer, some sort of recurring neural networks, and a bit of mycelium based uh, biocomposites, which is biodegradable. That's all I've got. Not much. Hopefully, I passed the QA. Wish me well. Okay. 9.58. A horizontal tube of 12.5 mm diameter with an outer surface temperature. Horizontal tube. Okay. That's how we are going to read. Okay. So one is horizontal tube. 12.5 mm diameter, outer surface temperature of 240 degrees Celsius, is located in a room with air temperature of 20 degrees. Please note the surface temperature is constant at 240 degrees Celsius, right? And air temperature is also constant at 20 degrees Celsius. The diameter is 12.5 mm. Estimate the heat transfer rate per unit length of the tube due to free convection. Again, very same, exactly same problem. This is how this whole chapter goes. I mean, you just have to use the equations, calculate the Rayleigh number from that Nussel number, from that heat transfer coefficient, plug in the equation, and then calculate whatever they're asking for. So let's use a black pen. I'll not stop. I'll not pause for this problem. I'll directly go for it. There's no need for diagram, but okay, let's draw. Horizontal tube, right? Something like this. My drawing is very bad. Horizontal tube. Surface temperature is located in a room with air temperature of 20 degrees Celsius. Heat transfer rate per unit length of the tube is to be determined. Okay. So one thing is you can say that the length is 1 meter. That way you will calculate the heat transfer rate per unit length directly. Okay. Another is you take any length L and then you finally divide by L and that's how you get the value. But simpler is use 1 meter approach. Okay. Mm, okay. So the the heat transfer rate from the tube would be how much would be it? Convection, right? Free convection. It is H times A times temperature difference. Very, very simple. Always Q dot is h times as times ts minus t infinity. This is the standard equation. Now we'll have to think what is as, we'll have to think what is h, we'll have to think ts minus t infinity. Okay, so uh, again we'll have to use the Rayleigh number and then Nusselt number, and then that's how we are going to calculate. Finally, what they're asking us to calculate the heat transfer rate. So q dot is the thing which they're asking us to calculate. Do we have q dot? We don't have. This what we have to determine. Do we have h? We don't have h. Do we have as? Yes, we have. Do we have ts? Yes, we have. Do we have t infinity? Yes, we have. We have everything except these two values, this and this. So again, let's calculate the Rayleigh number. Very, very standard solution. So Rayleigh number at any length L would be G times beta times Ts minus T infinity times. So for a cube, the L is D. If you don't accept my version, just calculate. It is A over P, right? Area over the perimeter. That's how you're going to get. You're going to get diameter itself. So D cube over nu times alpha, which is 9.8 times beta is how much? They might have given beta. Yes, 1 over TF. Uh, 2.5 times 10 to the power minus 3 times Ts minus T infinity, which is 240 minus 20 times dq, which is how much is, okay, 0.0125 raised to the power 3 over nu times alpha. Nu is 26.41 times 10 to the power minus 6. And what is alpha? Alpha is 38.3 times 10 to the power minus 6. Okay. So the value for Rayleigh number which I have got is 10410. This is the Rayleigh number. Very cute value. Now, from this Rayleigh number, we are going to calculate the Nusselt number. Okay. Now, again, which correlation that we'll have to check. It says horizontal tube, surface temperature, horizontal surface constant temperature. I think we know the equation. Horizontal cylinder, um, constant temperature case. Yes, it is on page number 52 of the PDF. Table C.2.1. It says NU is NU raised to the N. Okay, I'll write it that way. NU is 0.6 plus 0.387 times Grashof number times Prandtl number. I'm going to say Rayleigh number over 1 plus 0.559 over Prandtl number raised to the power 0.5625. Won't matter much, but still. Raised to the power 1.777, and this raised to the power 0.167, and this raised to the power 2. Okay. We have been given Prandtl number as well in this problem. Here is the Prandtl number. Okay. So you'll plug it in from here to here. Okay. So, okay, once we have this, I just have got the final value for the nozzle number. Oh, my thing became unstable because I clicked on ink replay. My bad. Should not have played with such stuff. Anyways, the nozzle number value which I have is, how much is it? It is 4.40. So it is pretty low value for the nozzle number. Let's call this equation 2. So probably in your examination, if you get few values correct, let's say you get relay number correct, you get nozzle number correct, you use the correct correlation, you might get partial marks for such stuff if you end up getting a wrong answer for the final problem which they are asking, the final variable. So NU, then very simply H bar at L is K times NU at L over D, D, right? Or LC, which is D. So how much is K? K is 0.0338 times, how much is NU? 4.40. How much is LC? LC is D itself, which is 0.0125. So from this, we are going to get H as 11.9 watt per meter square Kelvin. Okay, now we have H and we have this as well. Let's call this equation star. Let's call this equation 3. So from star and equation 3, we get uh, no, this is not star. Okay, let me rub it. Star is this one. This is equation star. We get Q dot is equal to 11.9 times AS, which is pi times D times L, right? And L is 1 because it says per unit length and we assume the length is 1. So pi times what is D? D is 0.0125. So this area times temperature difference, which is 240 minus 20. If you calculate, you're going to get final answer as 103 watts. This is the final value. And you must preferably write per unit length. Okay, that's it. I mean, we are done with the problems for today. If is there anything which is unclear or any other doubts apart from this? Okay. Arfan, I'm sorry you got stuck with me today. I mean, you had to bear with me for such a long time. But thank you for joining. Yeah, see you next week. Goodbye. Thank you for joining. Stop share. Yep, thank you for good wishes for my examination. See ya. Bye.